So if it is not an upper bound for set P, what does it mean? There exists some R in the set P such that X alpha is smaller than R. Okay. And if I want to put this R on this picture, where does this R is going to be? Between X alpha and S. Why it should be, can R be after S? Why? As a supremum actually. So since R is in P and S is the supremum of P, so R has to be inside this interval X alpha and S. R can't be here. Because if it is here, then S is not supremum. Are you getting the point? So R must be here actually. Somewhere here. Okay? R is somewhere here. Are you getting the point? Here's an interesting thing. So we are almost done with the factor step. Just think about it cleverly. So since R is in P, what does this mean? Since R is in P, what does this mean actually? What does this mean? What is the definition of something being in P actually? So if something is in P, then from A to that something, I can find a finite subcover. So since R is in P, this means that from A to R, I can find a finite subcover. Agree? I can find some finite subcover. In other words, I can find some O1, O2, O3, so on and so forth, On, that is going to cover everything from A to R actually. And here's the question, give me a finite subcover for A to S now. We're done with the proof now. Give me keeping in view this picture, give me a finite subcover for A to S. That's this way.
A minus epsilon से लेके सर y alpha तक कैसे?
Yes, I mean this is precisely what I'm saying. So if in this part I include this open set which contains S. So in other words, if O1, O2, On, if I add O alpha in it, just think about it. O alpha is going to be what? It's going to be things from here to here. So these n plus 1 is covering everything from A up to Y alpha, not B, Y alpha. And since this is covering everything from A to Y alpha and excluding Y alpha, okay, so it's going to cover also A to S. For sure, because S is in this interval. Are you getting the point? So let's put it as R in P. So there exists O1, O2, some On, a finite subcover of A to R. Okay? Hence O1, O2, On, and adding O alpha into this collection is a cover for A to S. Is it going to cover A to S? Think about it. It's indeed going to cover E to S. Okay. And if this is the case, what does it mean? This means that S is in B. S is in B. Okay? S is in B. Okay. So we're done with this step. So let's do this step 3. Let's do this step 3. Maybe we can begin step 3 from here. What is the step 3? That I want to show that now F is same as B. Isn't that a clever trick? Just think about it. Covering the part, finding the supremum, and then saying that that supremum is B and hence you're done. Very clever. Very, very clever. One who first thought of this proof must be a very clever guy. Anyway, so S is B. Why S must be B? This is what that we wanted to see. So S is a number, B is a number. What could be the potential relationships between S and B?
S will be less than or equal to B.
So we can have this that they are equal. S is bigger than B or S is smaller than B. Okay. So why S is bigger than B is unreasonable. S is supremum, so
Because this interval is bounded by B.
why S bigger than B
S bigger.
is not even a case that we shouldn't consider actually. Because B is upper bound actually for the set E. And S is the supremum of B, so it can never go beyond B. It has to stay less than or equal to B. Okay? And I'll prove that S less than B is going to create problems. It's going to give you contradictions. Okay? Hence, the only reasonable choice that you're going to have is that S must be equal to B. Okay? So let's see whether this works or not. So I'm going to say that suppose contrary. Okay. Suppose contrary that S is less than B. Agree? I'm going to assume the same picture as previous one. We haven't lost it. So I'm going to say A is here and B is here. Okay? And S is somewhere here. And this is my X alpha and this is my Y alpha. Okay. This is my X alpha and this is my Y alpha. So this is a picture that I'm taking with me. So S and Y alpha are two numbers. By the way, can I find a third number between these two numbers? Is it a difficult thing to find third number between these two numbers?
Average.
Okay. So I'm going to say that since as S is smaller than this Y alpha for sure, so I can easily find a number, maybe S prime, okay, which belongs to the interval S and Y alpha. In other words, this S prime is neither equal to S nor equal to Y alpha. So it's strictly inside here. Okay. This is a very troublemaking thing. This is a very troublemaking thing. What's a contradiction? Think about it. Come on. Okay. Let me put. Okay. So see, the previous picture is still valid. So if S is supremum and X is smaller than, okay, S, then I can find R in the interval P. I can find R in the interval X and find S, such that, okay, that for A to R, so from A to R, I have a finite subcover. So S is less than Y alpha. So I have this. So for A to R, I have a finite subcover. So what would be that finite subcover? O1, O2, On. And I'm saying this O1 to On, add this, what do you call O alpha. Okay? This O alpha. What's going to happen? If I added O alpha, what's going to happen? So if I have O1 to On, which covers from A to R, and I add O alpha, then this is a finite subcover, not only from A to S, but it's also a finite subcover from O to S prime actually. Is it making sense? Let me make some space and think about it. O alpha starts from where? So it starts from here and ends here. This is my O alpha. Now tell me that O1 to On is covering A to R, because R is in P. It's also covering A to S, because S is in P. We just proved it. But unfortunately, it's also covering A to S prime actually. So what does it mean? S prime belongs to P. But wait a minute. S prime is bigger than S.
Yes.
Wow, you found something which is bigger than your supremum in the set actually. So it's a straight contradiction. Is it making sense? So you see, the pictures says most of the things. Okay. Even if you read this proof from, what do you call primer, it's horrible proof. It's horribly written proof basically. But I like this pictorial proof because you can see everything. Anyway, so you got this. So let's precisely formulate. As I said, don't believe picture surface. Precisely formulate what we want to say. So as f is smaller than y alpha, so there exists some s prime in the interval s to y alpha. Okay, s to y alpha. Now, from S2, it's step 2, O1, O2, On, and O alpha covers A to S, okay, but it also covers A to S prime. Okay? It covers A to S prime. Why? Because this n plus 1 set of open sets are covering everything, from A up to Y alpha. So S prime is included. Okay? This implies S prime belongs to B. But, and obviously, and indeed, S is smaller than S prime. So that's a contradiction actually. And this is a contradiction. Contradiction to what? Contradiction to the fact that S is supreme. That S is supreme. Okay. So done with the difficult part. So from now on, we know that all closed intervals are compact. Okay? All closed intervals are compact. And now we can attack Heine Borel theorem directly. Okay. So let's do it. Okay, so I get rid of it. So we will prove this Heine Borel theorem. Theorem, we call it, in a series of lemmas. Put those lemmas in a proof, it will be better. Okay. So what was the theorem? Theorem was that K subset of R is compact. Okay, let's put all proof in a single basket. K subset of R is compact if and only if K is closed and okay, K is closed. Let's prove this side first. Okay, let's prove this side first. In other words, assume that K is closed and bounded, and we want to show that K is compact. Okay. So how can I begin with the proof of compactness? How can I begin? So I need to take up open cover. Select O alpha such that alpha belongs to R, Bn, open cover for K. Okay. It's an open cover for K. And what we like to show that what is given to me? It's bounded. What is the meaning of being bounded actually? there is an upper bound, there is a lower bound. In other words, I have a closed interval which begins from, for example, lower bound up to the upper bound that covers K. So since K is bounded, so there exists a closed interval A to B, okay, such that what? That K is contained in B. Okay. So can you see where I am heading? Where I want to go? What do you think? Obviously I want to go for the compactness of K.
But finite collection of subnets of curves.
Okay, obviously finite subcurrent. So that's what I want to do actually. I want to verify that, for this cover, I can find a finite subcurve. Okay. But what's the point of bringing in this open interval, closed interval here into the picture? Because we just showed that the closed interval A to B is compact. So what I want to do, so somehow from the compactness of this interval A to B, in other words, I'm going to find a finite, just think about it. So if I can have now, what do you call, a cover for A to B, okay, which includes these. So if I can have roughly cover for A to B, since this is a compact set, I'm going to get a finite subcover for A to B. But since K is included in that A to B, so that finite subcover is also going to cover K actually, because it's covering the big set. Okay. Big set. Here's the question, key question. What is the cover for A to B? This is certainly not a cover for A to B. Why? Because it only covers K. So what should I do with this actually? Here's the thing. Here's a picture. So this is my A to B. And K is something here. I don't know how does it look like. K is something like that. It's not necessarily that K must be an interval, could be union of interval, could be any crazy thing. It could be a finite set actually. So you know that. Okay, it could be a closed and bounded set. So I have only thing that covers this part. And I want something that now covers also A to B. So give me a cover for A to B. Think about it. So this thing and this thing is like my K actually, roughly. And I have this over alpha as a cover for the K. And it's not covering A to B. So what should I add more into this cover so that it can cover A to B? What do you think? Yes. So see, what we want to do, we want that I must have a cover which kind of covers everything from A to B. So what is missing? Okay. What if I include, this part and all this missing part into, the open curve? And what is all this missing part? Let me be precise. So I'm saying consider a V which is R minus K. R minus K. Is V open?
Yes, sir.
Why? Because
K is
it's
K
closed
is
actually.
Yes.
So V is certainly open. So I'm saying V is everything except this K actually. So it's going to include this part and this part as well actually. It's going to cover everything.
Yes, the intersection.
Okay. So now what does it mean? Then this O alpha such that alpha in I union V is a cover for it. Agree that if you include this V into this cover, so now I have an open cover. Okay. Now I have an open cover that covers your A to B. In fact, it covers whole of R actually. Not R,
No, sir.
not necessarily R.
It's not.
Okay. Excluding A. No, it is going to cover whole of R because this is covering K and this is covering K minus R. So it's covering whole of R. Hence, in fact, the particular case is going to cover A to B as well. Okay. Now, since A to B is compact, A to B is compact. So for this cover of A to B, I can find a finite subcover. Compact. So there exists a finite subcover. Okay. What would be that finite subcover? O1, O2, I don't know, ON actually, something like that. Now, what is the meaning of this? Of A to B. Okay. What is the meaning of this? When I am writing this, do you have any trouble with this? Or it's an okay argument? So see, this is the cover. Now, this cover has two kind of sets. Number one, O's and V. O's and V. Now, in finite subcover, maybe you can get sets from, maybe it is possible that the only some finite sets from O's can cover the interval A to B. R, I need to add V actually. So if I add V, it is still finite actually. It is still finite. It's nothing wrong with it. Okay? It is still finite. It's finite because these are n O's and that's n plus 1 open set. So that in total we have n plus 1 open set. That covers A to B. Okay? Cover of A to B. But the same cover as K is included in A to B, okay? So the same